All right, good morning, everybody. Let's get started. We are partway through our second to last theme of the course, looking outward, thinking about designing technology that we deploy out into the real world, that is sensing the real world in real time, not unlike how we are. We are trying to instrument design that technology in a way that it disappears into the background and helps us carry out tasks that would be difficult or impossible to carry out otherwise. We're going to finish lecture 19 today when we're looking, which will finish our three-part series on looking at ubiquitous technology that tries to help us answer questions about human or social behavior. We looked at how people tend to interact face-to-face and how their position within that group alters their behavior in those face-to-face interactions. We looked last time at this what's now grown into a subfield of HCI, which is activity tagging, tracking your behavior throughout the day, and trying to add some machine learning to predict, given those raw measurements, whether whatever it is you're doing is positively or negatively affecting your physical or spiritual well-being. And we started last time by looking at the somewhat controversial human speechome project. How do children acquire language? It's a very mysterious topic, very difficult to measure and understand. Up until recently, psychologists have tackled this problem by bringing the child and parents into a laboratory setting, which is by definition an artificial environment. So anything you do learn in a lab setting may or may not tell you something about how children actually acquire language in the wild. And by in the wild, we mean usually their home. Right? So we're going to continue on looking at Deb Roy's speechome project today, where he and his wife actually instrumented their own home and tried to record as much as possible about the first few years of their child's life, and then use that raw data to actually start to answer these questions about how children acquire language. We'll finish that up, and then we'll turn to a four-part lecture series on robotics. Why are we talking about robotics in an HCI class? We've spent a lot of time in this class talking about interaction in the sense of an intelligent being. Usually it's a human user that is pushing against the world or pushing against a technology, literally or metaphorically, and observing how the technology pushes back. We've spent some time talking about embedded devices and ubiquitous technology, which also observes the real world, but has limited ability to push back against the world, to actually cause change in the world. We can think about wearable technologies like a Fitbit in the case of activity tagging, where the technology is sort of passively riding along with the human operator and picking up information along the way. What's going to distinguish robotics from the other ubiquitous technology we've talked about before is robots have motors. They are able to act on the world independently of their human operator or owner and observe how the world pushes back. So we're going to switch from talking about human-computer interaction to human-robot interaction, robot-robot interaction, and all of the more complicated interactions that arise when we start to instrument our world, not just with sensors, but also with active technology that, like us, can also push against the world and observe how the world pushes back. Okay, that's where we're going. You've made it. We're at deliverable 10, the 10th and final deliverable. So let's talk about deliverable 10 for a moment. You are going to be filling in the fourth and final panel here in the lower left. Some of you may have put material from deliverables 8 and 9 in different panels. Doesn't really matter for our purposes which panel you place your visualizations in. In this final deliverable, you're going to be creating additional visualizations, but these are visualizations that are running continuously throughout the user interaction, like the skeletal hand up here. And these visualizations are going to give real-time feedback during a single user interaction. So you're going to be creating in deliverable 10 3 different real-time visualizations. The first one is going to show how the user's performance during the current session differs from their performance differs from their performance from the last session. So how am I doing now compared to the previous session? That's deliverable 1. And again, you can choose however you wish to do that. Shoot a video of that visualization. Second visualization, how does the user's performance over all sessions compare to the performance of other users? How am I doing compared to other people that have used the system so far? Third and final visualization is real-time feedback about a single-digit presentation. So as you know, but as your user may not know, it takes the KNN algorithm a few iterations through the infinite loop to detect whether they're signing the digit correctly or not. What should your user be doing during that period? So you're going to be creating some kind of warmer or colder visualization at this point. So the system asks the user to sign the gesture 1. The user signs the gesture 1, but for whatever reason, the leap motion device is detecting an occlusion and it's not predicting 1. So the prediction of the KNN algorithm is not matching the digit that the user was asked to sign. So the visualization should say colder. The user should change what they're doing somehow. Or they're getting warmer. The predictions are correct. Give the KNN a couple more cycles to ensure that you're actually signing the correct digit and that it's not just a hiccup in the KNN or the leap motion device. And then you've signed the digit correctly. Sound good? Pretty straightforward? Any questions about that? Okay. Next week, we will talk about what you'll be doing post-deliverables, which is these interim videos, 1 per week until we get to our final exam period. We'll talk about that next week. Any questions about deliverable 10? All the other 9 deliverables? No? Okay, so back to the Human Speechome project. So just as a reminder, this was a question about trying to answer the question, how do children learn language? And to think carefully about the physical, social, and cultural contexts that surround that activity. And hopefully, in this case, it's quite a bit of instrumentation in the home, but trying to do this in an unobtrusive manner as possible. This was work done back 10 years ago. We already talked about this a little bit. Okay, so we watched the video last time. In the first part of the video, this was Big Daddy, right? The parents being able to observe everything about the children. Part 2 of the video was sort of Big Brother. How do you monetize that process by watching all channels and all social media feeds? Maybe that's not so important for our purposes today. Okay, so let's talk about the technology first. They mentioned this throughout the TED Talk. They instrumented 14 microphones and 11 overhead omnidirectional cameras. So the cameras are up there in the ceiling, and hopefully the parents and the children forget about the cameras. And the nanny, there were 3 caregivers. Now, they probably didn't forget about it all the time, so there were probably subconscious or unconscious influences on their behavior around the child, knowing that video and audio was being recorded. So again, this isn't perfect ubiquitous technology. It's not perfectly invisible. 11 overhead cameras, 14 microphones, and you could see from the video the kind of video and audio they received. They collected data over the first 9 to 24 months of age for the child, which is known to be the most sensitive period of language acquisition. This is when the child acts like a sponge and soaks up a huge amount of language, and for most children within this period starts to regurgitate those words back to the caregivers. During this period, they collected over 4,000 hours of recording, over 444 of those 488 days. So they didn't get every single day. You can imagine there were days when the video or the audio went down or something else happened. Obviously, they're not capturing all hours in the home. What else is this massive dragnet missing? We're trying to capture as much data as possible about the child during this sensitive period. Of course, it's not perfect.
When the When the child is outside.
When the child is outside, of course, right? So it's not perfect. There's lots of missing parts here, but again, as Deborah mentioned, this is the biggest family album of all time, right? The most data that's ever been collected about a human child during this sensitive language acquisition period. About 10 hours of recording per day. They captured, they think, between 70 and 80% of the child's waking time. And 5 to 6 of the cameras were active at any time, right? You could imagine the child in room 1, the parent in a room next door. There's an open door between the two rooms. The parent is saying something, and then a few seconds later, possibly the child says something else. There's yet another caregiver in a distant room. So there's obviously lots going on in the home. Complex social dynamics going on that we're going to try and capture and analyze. Okay, so just as a reminder, we mentioned this last time, most work in psychology is theory-laden. I have a theory about how children acquire language. I bring them into the laboratory and design and conduct an experiment to test that theory, positive or negative, right? Why do we do this? Because, of course, we can't instrument every waking hour of the child's life or a human subject's life. But with the advent of unobtrusive, ubiquitous technology, we may be able, as scientists and psychologists, to free ourselves from the theory trap. We might be able to just let humans do what humans normally do, and assuming they're okay with it, capture as much data as possible, and then try and ask questions about human behavior from a data-driven approach rather than a theory-driven approach. Capture the data and then dive in the data from different theoretical perspectives. So I can come to the data then with a theory and look to see whether the data supports that theory. And hopefully we're doing this in a much more natural setting. And what we do learn from the data might be closer to the reality of human experience and human development. That's the idea or the hope for ubiquitous technology in the psychological sciences. Okay, so back to the Human Speechome Project. We're going to break this down into 3 phases. First of all, there's the raw capture, right? We're trying to capture as much audio and video, at least indoors for the child, as possible. Given that massive raw data set, can we then distill it down into a number of features? So you remember back to your KNN algorithm, we had 4 features in the case of the flower, 120 features in the case of the human hand. But those 120 features about bone position came from a much larger raw data set, which is the raw infrared pixel values coming from the device itself. So the Leap Motion device distills down raw data, raw infrared data, into relevant features for inferring hand position, which is bone position. We're going to do the same thing here, but at a much larger scale. We're going to take the raw video and audio and try and distill it down into relevant features, such as language from audio, people from audio and video, activities and objects. And if you're paying close attention, you'll notice during this first transition from raw data to features, theory is already starting to creep in, right? We just said we want to try and keep this as purely data-driven as possible, but we're already introducing unmentioned assumptions about language acquisition, which is that language acquisition is most dependent on language. Maybe that one's not so surprising. But also people, activities, and objects. So there's certain things that are going to be left out of the raw data that may influence language acquisition that aren't captured by these features. What might some of those missed features be? Most likely a child's first word is going to be influenced by hearing that word on the television or hearing the caregivers mention that word. Who said the word? What were they doing when they said the word? Which room were they in? What objects were they holding or what objects were they looking at when they said that word? What else might matter here?
Seeing the faces and how they make the words and the letters inside of the mouth.
Okay, so it's obviously not very specific here. What about people, right? Is the video, the inference of people in the video, is it going to be sufficient to see whether the child could see the face of the caregiver speaking the word when the caregiver spoke the word? Maybe yes, maybe no. Are there features other than people, activities, and objects that might influence the child's language acquisition that may be in that raw data but are being thrown away here? Are we missing things or losing things? You're all excellent English speakers, but you're also learning a lot of new things. Think about acquiring new knowledge here on campus. What aspects influence whether you absorb class material well or not? Time of day, right? They have that. It's not captured here, right?
How much sleep you got?
How much sleep you got. Now you might be able to capture that from raw data of the people. They were capturing 70 to 80% of the child's waking hours. What about the child's non-waking hours? Do they have that in the raw data? Do they have it but they're throwing it away? Theory is already creeping in, right? We could, of course, assuming we were able to get access to the raw data, dive into the raw data with new theories such as time of day and sleep influence language acquisition, and try and distill those features out of the data and try and answer questions about language acquisition in that way. This is, again, all ongoing work, right? How can we capture as much of the features as possible that might influence a particular human behavior, such as language acquisition? Okay, so again, once they have those features, and they're going to focus on these 4 classes of features, can they prove or disprove theories of language acquisition? So from the audio, they're going to try and pull out who was saying what and how. That's prosody. Remember, it's very important, not just what is said, but how it's said. And we'll look at how they do this in a moment. We did a lot of speech transcription, speaker identification, so not just identifying English words in a raw audio stream, but who said it. Prosody features, again, how is it said? And from video, they're going to try and get at people and activities and objects, right? Who was where, what were they doing and how, with what kinds of objects. So going back 10 years ago, person tracking and identification was not as sophisticated as it is now, but it was still possible to some degree. What were they doing? So like we just saw in the previous activity, they're going to try and, the previous lecture, going to try and do some activity classification. We're assuming that the caregivers and the child did not have a Fitbit at this point, so there's no acceleration data. We don't actually know how they were moving or what they were doing. We're going to try and infer it indirectly from the video and object tracking and classification. So we're going from the raw data to machine perception. We're going to try and automate the distillation of raw data down into features as best we can, but it was, again, very much a black art back in 2009. They're also going to incorporate some human analysis into this loop. Once they have the features, they can start to do some machine learning and make predictions about child learning. So, for example, we could propose the following hypothesis: that when a word was spoken by the child for the first time versus how often was the word spoken by the caregiver. I hypothesize that frequency of the word being spoken is going to influence when the child speaks the word for the first time. Seems kind of intuitive, right? The more the child hears the word, the earlier they're likely to utter it themselves. It's a theory, but I'm going to try and use the data or the machine learning and look at these features. Pull out of these features frequency with which the word was uttered by caregivers, and also the time at which the word was spoken by the child for the first time. Okay, so let's look at audio now. So this work was carried out in the MIT Media Lab. The Media Lab is well known for doing a lot of HCI pioneering work. So on top of this raw data, they had to create some HCI interfaces to be able to perform some very challenging tasks like scan through 9 months to 24 months, so 18 months worth of raw audio, and pull out of that words which obviously exist in that audio for just a few seconds. Right? They're going to look for needles, 2 or 3 second utterances in a haystack, an 18-month raw audio feed. How do you do that? Well, one way is to start doing a visualization and designing a particular visualization to help with a particular task. Remember our PACT analysis. So the task here is finding needles in the haystack, finding words in 18 months worth of raw audio. You can visualize audio well using a spectrogram. So what is a spectrogram? Well, as you can see here, on the horizontal axis, we have time. On the vertical axis, we have frequency, from low frequency to high frequency. And the amount of ink that's dropped at any one point is the power, the amount of that frequency in the signal. You can get very good at reading spectrograms, and you can see speech versus non-speech, white noise versus a repetitive pattern like a song. You can actually see the things that the particular types of audio by visually scanning images. Why would we want to take audio and turn it into video when we're looking for words in the audio? Why this particular visualization decision? Why the decision to visualize audio at all?
You don't listen to all of it, so now like make noise.
Exactly. So again, back in 2009, you couldn't just pull words out of a raw audio feed. You had to either listen to 18 months worth of it and pull out the words, or compress that time into spectrograms to allow someone who's good at reading spectrograms to zoom in on a 30-minute period in which there's lots of word footprints, right? So you could look at, if you're good at looking at a spectrogram, you can look at a 4 or 5 or 6 hour stretch and see a lot of sound, but focus in very quickly. That's where there was a conversation, right? Okay, so good reasons for doing that, and obviously they need to do this across the parallel microphones that are picking up sound throughout the house. They put in lots of nice interface features so that you could zoom in to a few seconds and actually identify and then listen to that audio to see if there actually is a word uttered during that period. Scan back out to a few years, months, weeks. Not an easy thing to do, right? A very challenging task. A lot of interesting HCI challenges there. Once they started to pull out shorter audio tracks, someone had to actually listen to those audio tracks to identify, yes, there's a word in there, and yes, the automatic speech transcriber got it correct. Not an easy thing to do. So about 25% of the audio recordings, when there actually was sound going on in the room of the home, was speech. That already is kind of interesting. They would then select a segment of speech or potential speech to be transcribed, listen to the segment, and type what was heard. This was a very time-consuming, not that interesting task. They tried to automate it as much as possible. So it's a little hard to see here. Let me see if I can zoom in on this for you. So here's a little snippet of time in which either the parent is singing to the child or the child is possibly watching television, and the automatic transcriber thinks that the wheels on the car go so fast was mentioned during that time period. The transcriber is listening and ticks off, yes, that's correct. Part of the speech was clipped. Was it television? Was it actually one of the speakers? It's not clear. I don't know. So sort of annotating and correcting the automatic speech transcription. Okay. Using today's technology, this would probably be easier, but if you've ever used automatic speech transcription, it's still not perfect. Okay. Okay, so again, there are a lot of other HCI challenges where they try to help distill all this down to features. Once they do, then we can move on to the third and final phase, which is the science part of this, and start to ask and try and answer hypotheses about language acquisition. Here's one particular graph that they pulled out of these features. We've got the age of the child on the horizontal axis here. And for each month, they asked how many word births were there. During that month, was there a word spoken by the child, an adult form of the word spoken by the child for the first time? At age 9 months, the child uttered 2 or 3 words for the first time. At 17 months of age, the child issued 35 new words during that month, and so on. Tell me about the language acquisition for this particular child during this period. What happened? Assuming that our feature detectors and machine learning algorithm is relatively accurate, how is this child acquiring language during this period?
So before 20 months, the child is learning faster and faster, and then past 20 months, it's kind of the speed is decreasing.
The speed is decreasing, right? So this part of the curve is not surprising to most developmental psychologists. This is the canonical sponge phase. They are absorbing words and regurgitating them back at an ever-increasing rate. A lot of words in the English language. What was a little more surprising is this sudden transition where acquisition drops off. The rate of acquisition is still positive. The child is still uttering new words after 20 months of age, but at a much slower rate. Okay, so one hypothesis leads to another. What's happening here?
You only need a few hundred words to be able to communicate.
You'll need a few hundred words to be able to communicate.
So after that few hundred words, where people understand what you want, after that, just describing better what you want. Your vocabulary is just improving at that point.
Okay, right? So why does a child observe and regurgitate so many words? So that they can articulate what they want. That's a pretty common hypothesis across the developmental psychological realm. It drops off because...
But why is a spike?
Why a spike?
Yeah, because if you have enough words to communicate, it's like a gradual thing.
The spike is a little mysterious, right? Possibly this is an artifact of the data. Maybe this is not quote unquote real. We have to take all of this again with a grain of salt. We know there's a lot of noise in this process, right? The raw data itself is not capturing everything. It's not capturing everything perfectly. Our distillation of raw data down into features is not perfect. So again, we need to treat this with a grain of salt. But there definitely, we can trust that there is an exponential increase and definitely a decrease during this period. You mentioned vocabulary. What about this decrease? What could explain this decrease?
I think it's because once you kind of learn a good basis of words, you kind of have like almost like a good base for your brain to start learning other things too.
Okay.
So your capacity to learn like goes up, so you may not be learning as many new words, but your brain is learning more overall.
More overall. So what might the child be learning above and beyond just new words? What is it that they're doing during this period?
Maybe like social interactions.
Social interactions, of course, right? There's a lot for a child to learn during this period.
Maybe grammar.
Grammar, right? The power of language, of human languages, is its combinatorial power, right? I want more. More is a good word. You can imagine that one's in there. I want more water. I want more food. I want more attention. I want more sleep. I want more of being left alone. It's the combinations, possibly, that the child is experimenting with during this period. Possibly, at this point, the child has enough words where now the child is possibly subconsciously realizing that you can get more of what you want, not by uttering new words, but combining them in new ways. Again, that's just a hypothesis. We could imagine diving back into this data to see whether the data supports that hypothesis. We could, for example, instead of plot word births, we could plot word pair births. When does the child say more water for the first time? Okay, let's look at another hypothesis. I mentioned this one a few slides back. Does the frequency that a word is heard predict how early the word is spoken? So on the horizontal axis, again, we have age and months of the child. And on the vertical axis here, we're going to have the frequency, or how often the word was heard, how often the word was spoken by a caregiver, the mother, the father, or the nanny, within earshot of the child. It's log frequency. For our purposes, that won't matter too much. So for example, a point down here in the very bottom right represents what? What does this bottom rightmost point represent?
A word that was never really said by the caregivers, and then the child learned it like 24 months.
Exactly, right? That word was uttered by the child only for the first time after 24 months and was never heard by the microphones. The child probably heard it, otherwise how did the child utter it? But it was either spoken by someone else, in a room, outside the times during which the microphone was on, or outside the home. Maybe it was on the television, but it was out of earshot of one of the microphones. Who knows? Versus a point up here in the top left. So here was one of the first words that the child ever spoke, and that was uttered very frequently by the parents. If we then linearly regress this red line against the data, so we try and place this red line in the plane so that it is as close to all the dots as possible, you can see this is kind of almost an impossible task. There's quite a bit of spread in the data. However, it is a pretty good fit, and we won't go into the p-values, but it's a good enough fit to give a negative slope, which means obviously that the lower down, or the less frequently the word was heard, further to the right, the later it was for the child to utter that word for the first time, right? Kind of makes sense. Again, it's not a good fit because, of course, language acquisition is an incredibly complicated phenomenon, and it's doubtful that any one feature, like how often the word was spoken by the caregivers, is going to perfectly predict when a child utters the word for the first time. But it looks like it's at least part of the story. Right? Makes sense. What else besides frequency might predict how early the word is spoken? I know there's a few parents here.
Maybe the simplicity of the words.
The simplicity of the words, right? What words did the parents speak? What else? We've looked at a few language applications now. What are some of the other aspects of speech that might predict how early the word is spoken by a child? Think about, again, the physical and social context going on in this house between 9 and 24 months of age for the child.
And maybe now is probably earlier than verb and
nouns and verbs, yeah, possibly.
and
We could split the words into nouns and verbs. Maybe one or the other is easier for the child and the child utters it earlier. What else? So those are features of the language.
Like a reward structure, so you reward them for saying mom or dad, but you might not say reward for as or for.
What about reward, right? What happens in the seconds or minutes after a child utters the word for the first time? What kind of rewards might the child expect to receive? Food, praise, attention. The caregiver looks at the child immediately after the child utters the word for the first time. The parent's eyes widen in delight that the child has mentioned a new word for the first time. Lots of those subtle social cues are not obviously, but potentially underlying language acquisition. Let's add just one additional feature, which is prosody, how the word is spoken. So we're going to look now at F and P. F is going to represent the frequency with which parents uttered the word. And P is going to stand for a prosodic feature, so some feature of how the words are spoken. In this particular plot, they're going to focus on what's sometimes known as mommy ease. So when you speak to a child, some people will instinctually elongate the vowels. So we're going to measure this particular prosodic feature of mummy ease, where a P of 0 represents you speak the word in the adult form, and the longer the caregiver elongates the vowel, the higher the value of P. So far, so good? You can imagine that this is not something that's naturally captured by an automatic speech transcriber, so that these different kinds of P values were extremely painful to collect from the data. Luckily, they do indeed have an influence on how early or how late the child utters a word for the first time. Here's how we're going to look at this. We are hypothesizing that both F and P influence language acquisition, but we don't know in what proportions. So we're going to combine F and P together, and we're going to introduce a third parameter here, alpha. And you can think of alpha as a slider bar that we're going to slide back and forth between a value of alpha equals 0 and alpha equals 1. Alpha equals 1 is, we're going to combine all of F and none of P. So this is actually alpha times F plus 1 minus alpha times P. So alpha is going to dictate the proportion that we're going to combine F and P. An alpha 0.5 means mix F and P together in equal amounts, and an alpha of 1 is it's all P. So at any setting of alpha, we have some combination of F and P, and we can then ask how well, if at all, that combination correlates with language birth, right? The time at which words are born. Question?
What does it mean that that correlation is like negative?
So we can see that in this case. So for the value of alpha equals 0, we're looking whether there's a correlation between F, which is shown here on the vertical axis. Here's F on the vertical axis. And we can ask whether it correlates with the time at which the word was spoken for the first time. So a negative correlation value means negative slope, right?
Means it's spoken earlier.
Higher frequency means later acquisition. Lower frequency means earlier acquisition. Right? So we've got F on the vertical axis, time on the horizontal axis. The higher the F, the earlier the T. The lower the F, the later the T. That's an anti-correlation. They're related. There definitely is a relationship, but it's an anti-correlation, right? A positive correlation, an R of plus 0.29 would mean the higher the F, the more frequent, the later the child spoke the word for the first time. Right? So we're looking really to see whether there is any correlation, large negative or large positive. A correlation near 0 means there isn't much of a relationship between F or some combination of F and P and the time at which the word was spoken for the first time. Make sense?
How could you have a frequency of 0 with full prosody?
Okay. So here we go. So remember, so here's frequency on the vertical axis. So frequency is always going to have a positive value. Frequency of 0 means that word was never spoken by any of the 3 caregivers throughout this 9 to 24 month period of time. A maximum frequency, at least in this picture, is 9. So in this case, F is going to range between 0 and 9. Okay. Mommy E's, here P is also going to be a positive value, and it is also going to range from 0 up to some positive number. Doesn't specify here what it is. A P equals to 0 for a given word means that word was spoken by the caregiver in an adult form. A very high value of P would be how long they elongated the vowels. If we imagine a hypothetical theoretical transcriber that could actually take a raw audio and give you back the number of times that a given vowel in the word was duplicated, that could be P. P is the number of times that the vowel is repeated, for example, right? The more The longer the vowel is elongated in the audio, the more O's or A's or I's are captured by the transcriber, the higher the value of P. I doubt that's how they actually did it, but that's the basic idea. So P is basically how much the vowels are being exaggerated.
So if the frequency is 0, shouldn't that be a special case where the P is also 0, since it was never spoken, there can't be any elaboration on it?
Yep, good point. So for a given word that the child uttered, if we go back and look for the parent uttering it, and we find an F equals 0 is never heard by the parent, then P would also be 0. Yes, that's right. So far, so good? Okay, so in this plot on the left, we're comparing F against time and asking whether there is any correlation. In this case, there's a negative one. But of course, on the vertical axis, we could put, instead of F, we could put F plus P. For any given word, how frequently was it uttered? The F plus how much were the vowels elongated whenever that word was spoken by the caregiver. We could put F plus P on the vertical axis and ask whether that correlates with time. That example corresponds to alpha 0.5. So an alpha 0.5 mixes F and P together in equal amounts. You can just think about it as a weighted sum. And then asks, for that particular admixture, does it correlate with time? And if we go to this plot now on the right, we can actually find that admixture. So for an alpha of 0.5, we're asking, is there a correlation between F and P combined in equal amounts to time? And it turns out, yes, there is. There is a correlation of negative, whatever that is, negative 0.26. Correlation is a little bit less, a little bit closer to 0 than the correlation for just F. So far, so good? So the way to read this plot on the right is on the horizontal axis now. We're not plotting time. We're plotting different mixtures of F and P. I could make a hypothesis that says, I think word birth is most sensitive to 80% frequency and 20% prosody. Frequency is more important than prosody. It's a very specific hypothesis. I could ask that and then look on the vertical axis of 0.8F plus 0.2P and ask, if I fit a red line to that scatter of points, is it a better fit? If you do that for a number of different values of alpha, every point on this plot corresponds to a different weighting of frequency and prosody, and asking how well that weighting predicts word birth. And we get this check mark pattern. What does that tell us?
I guess the amount of 80% frequency, 20% prosody will basically, that gives you the curve of this will predict which words will be chosen.
Exactly right. So at this value, we can see there's a minimum in the correlation. The correlation is most negative at an alpha of 0.2. And we are looking for points that are as far from 0 as possible. The more negative or the more positive our value of R is, our correlation, the more that feature predicts the other thing, which in our case is word birth. So the correlation is strongest at an alpha of 0.2, and as you mentioned, that corresponds to 80% frequency and 20% prosody. That correlation is more than frequency alone or prosody alone. So for this particular child, whatever is going on, neither F nor P explain language acquisition, but a particular combination of F and P do a better job of predicting. So what do we learn about this family from this example? We know that the caregivers were elongating the vowels to some degree, and obviously emitting and saying some words more frequently or less frequently than others. And that was, both of those things were influencing language acquisition for this child. Again, that hypothesis or that finding suggests 10 more hypotheses, such as, we know that word acquisition for this child is influenced by frequency and this particular kind of prosody. What new directions does that take you in thinking about language acquisition?
How maybe this child compares to other childs, if different families have different relationships between prosody and frequency.
Absolutely, right? So thinking about social and cultural context, obviously what goes on in the home of any given child is very different from one child to the next. How consistent is this signal across children? Assuming we were to repeat this experiment, which I don't know if we want to do, how similar is this? Is it all human children tend to acquire language as some function of how often they hear it and how the caregivers pronounce it? Maybe yes, maybe no. At the moment, no one knows. If F predicts word birth and P predict word birth and both together predict word birth better, what else does that suggest to you? There's other factors, right? Here's 2 of them. There's probably dozens or hundreds or maybe thousands. Who knows, right? Okay. This is not a class in linguistics, so we're going to leave that here, and we're going to finish with this last plot, which already we saw in the TED Talk. This is just a good plot to remember. This is probably, in my estimation, the best example of scaffolding. You can actually see it in the data. So on the horizontal axis here, we don't have the age of the child. We have the months from word birth. We'll come back to that in a moment. On the vertical axis here, we have change in MLU, the mean length of the utterance. So for every word that the child uttered for the first time, between 9 and 24 months of age, we have that point. We can then ask when the child uttered that word for the first time, and then move backwards in time in the data set and find all the times before the child uttered the word that a caregiver uttered the word. And for every time we find that word, how long was the sentence that that word was embedded in? The parent says, "Do you want water?" Length of utterance 4. Want water? Length of utterance of 2. 4 plus 2 divided by 2 is 3. Mean length of utterance for water, given those 2 captures, is 3. Right? Okay. So if we then line up all the word births, so obviously the child uttered words for the first time at different times, we take all those words and we line them up at 0 on the horizontal axis. We get this very interesting pattern, which is around the time that the child uttered the adult form of the word for the first time, the parents were emitting 0, on average, 0 length utterances or around 1. So short, very short sentences. Water, or even half a sentence. Water, water. Very, very short utterances. 15 months before the child uttered the word for the first time, the parents were emitting sentences to the child that had a length of, on average, 2 or 3. Want water, you want water, and so on. After the word is spoken, there is a slight increase in the length of the utterances, again from the caregivers. So definitely, caregivers are changing their speech patterns in anticipation of the utterance of a word for the first time. Why? What's going on here? So it's definitely scaffolding, but scaffolding how?
That the baby's developed enough vocabulary already is figuring out how to form words without the needing for the elongation.
Without needing for the elongation? Yeah, okay, possibly. But why didn't the parents just, why isn't this line flat then? Why don't the parents just have very short sentences the whole time? Why is the line curved?
Can you clarify like, what mean length of utterance is? Is that how long they said, like how elongated? Or
Sorry, the number of words in a sentence.
Okay.
So a length of utterance equal to 3 is you want water. Length of utterance 4, do you want water? That's the length of an utterance. But we're capturing those sentences many, many times before the child says water for the first time. So we're taking all those sentences and taking the mean length of them.
So for this chart, the black line is a fit line, and for the change in MLU, and the red dot is the actual average with the 25 percentile.
Correct. So let's look at just this the farthest left red dot. The farthest left red dot represents the fact that for all words that the child spoke for the first time, 15 months before the first utterance of those words, the parents were uttering sentences with 2 or 3 words in them. Not just water, but all those words that the child utters for the first time. When we get down here, they're very, very short. 1, 2, 0. I'm sorry, I misspoke. It's not MLU, it's change in MLU. I'm sorry. Okay, let me start this again. So the dotted line represents 0 change in MLU. If we take all the sentences that the parents ever uttered with the word water in it, let's assume that that average over all those utterances was 3, for example. Okay? Up here, the change in MLU is 2.5, which means 15 months before the child ever mentions the word water, sentences that contain the word water 15 months earlier are 5.5. Right? They're 2.5 more than the average water sentences, which is 3. Make more sense?
So it looks like they changed their words more quickly in the beginning, or their sentences, or their sentence length in
Yes.
the beginning, and then that decelerated to, I'm assuming, would be 1 word.
Right, so remember that around here, around 0, it doesn't necessarily mean that the sentences uttered by the caregiver is 0 or short. It's the mean, whatever the mean was. Could actually be 7 or 8. This plot doesn't tell you anything about that. But it's definitely shorter than those sentences were long before the child uttered the word or after the child uttered the word.
Based on this, I would hypothesize that the child is probably learning the word long before the caregiver thought they were, and that once they started like doubling down and trying to really teach it to them, then they eventually actually.
Maybe. So word birth, right, is the birth of the word from the mouth, not the brain of the child. Very difficult to say when the child knows the word, right? You may be right. Much more difficult to get at that phenomenon. But why the curve? Why are the parents emitting longer sentences? If children learn better from shorter sentences, because the child uttered the word closer in time to shorter sentences, why don't parents do something similar to Mummy E's here? Why don't they just use very short sentences? They're not. They're doing something else.
Right, I think the quote from the last time is they're building the speech back up so that way they've got the grammar around.
The grammar, right? So obviously, we're trying not just to teach the child individual words, but how to use the word in combination with other words, presumably, right? Water is a powerful word to know, but want water, I want water, do you want water, that's more powerful, right? I can do more things if I combine words together. Maybe, again, we hypothesize, maybe that's what the parents are doing after word birth, which is helping the child understand how to put words together in combination. But what about before word birth? This is harder to understand. Why are the parents using longer utterances long before the child's even uttered the word for the first time?
My guess is that the parents have kind of certain goals in mind. So like maybe they were working on other words before, but then at this point they kind of hone in on teaching the kid water, and so that's when like the scaffolding comes in place.
They hone in on the word, on the child acquiring the word water, right? So the parents are starting to utter shorter and shorter sentences that contain the word water, and it gets to its shortest point, or the average length of the utterances, right when the child utters the adult form of the word for the first time. But how did the parents know to hone in on that word at that rate? So during the talk, Professor Roy says the parents swoop in or meet the child at the word birth. Nobody knows, right? But it seems that this is what's going on. There's definitely some scaffolding, right? The parent sees that the child cannot ride a bicycle, puts training wheels on. The parent is watching the child ride the bicycle with training wheels and is seeing something in the way the child is riding the bicycle, in the way that the child is possibly emitting child forms of the word water, which for this child was gaga. There's something about what the learner is starting to signal competence. And as the parents start to see or observe or infer growing competence, they reach in and they gradually are adding scaffolding. And then the child utters the word and starts to use it, and they're gradually removing the scaffolding again. So this is a pretty interesting finding. It seems intuitive that parents teach their children language, but what's more interesting is what seems to be going on is the child is teaching the parents how to teach it language. Right? The learning is bidirectional. The teaching is bidirectional here. Right? Somehow, what the cues are that are going back between the caregivers and the child, who knows? But this is one of the benefits of data-driven approaches. Right? It's unlikely that someone would suggest out of the blue the hypothesis, maybe children are teaching parents how to teach it language. That seems to sort of jump out of the data. Okay, again, not a linguistics class, but a demonstration of what ubiquitous computing and technology can help us with. Okay, any questions about lectures 17, 18, and 19 before we move on to our last class of technology? Okay. All right, so at the beginning of the course, we made this sort of cartoon of humans interacting with computers, human-computer interaction, and the idea was to think not really about where the interaction starts or ends, but to think about a continuous interaction where the output of one participant, like for example the movement of a mouse, the output of the human becomes the input to the computer. The computer senses change in position of the mouse, and then vice versa. The computer outputs some visualization to the screen, which falls onto the retina of the human, which alters the behavior of the human, and around we go. We are now going to start to look at a particular kind of technology, robots, which are active. They are able to actively act on the environment, and the robots can sense the repercussion of their actions. So we're going to get into a much more complicated loop here. We're going to speak in lecture 20 here about this particular feedback loop and understand how this works in robots. And then we're going to look at human-robot interaction, where humans become part of the environment of the robot. The robots are hopefully not physically pushing against the humans. They are metaphorically interrogating the humans and observing how the humans push back. Right? So we'll look at social robots next time. Okay, so how does a robot go about interacting with its environment? There is this continuous feedback loop, which is difficult to think about. And we talked about this at the beginning of the course. It's much more intuitive to think about a passive being like a human or a robot that sits there and waits for some input from the world, cogitates and processes on it, and then does something. It's not that simple. There's a continuous feedback loop. One is always pushing, both are always pushing, and the other participant in this feedback loop is always receiving that push. Because that's non-intuitive, in the history of robotics, we've tended to look at animals as being overly complicated than they actually are. We talked about this at the beginning of the course. So we looked at B.F. Skinner's box, which was a way to put an animal in a box and try and simplify the behavior of the animal to really understand this feedback loop. One of the repercussions in the field of robotics is because we tend to overestimate the complexity of what's going on in the head of the animal or the human, we've tended to try and create overly complex robots that fail. So one of the reasons that robotics has not moved at the same pace as computer technology is because of our inbuilt bias to understanding behavior. Most roboticists would like to take human or animal behavior and build it into a machine. But if we overthink that behavior, if we think that behavior is overly complicated, we build an overly complicated behavior into our robot and it fails miserably. So the HCI approach to robotics is to think not so much about what's going on inside the head of the animal or the human, but to focus instead on the interaction. If we can get the interaction right, we can get away with simpler robots that still do what we want them to do. So again, just a reminder of this idea of mental model. If you observe an ant moving along a beach, it will carve out a very, very complex path, and you might be led to the assumption that that ant is doing some very complex navigation, instead of what it's probably doing, which is interacting intelligently with the beach, which is if there's a stone to my left, go to my right. If there's a stone to my right, go to my left. If there's nothing in front of me, go straight, right? We're talking about stones and the ant's immediate environment. We think about the way in which the ant could interact with its environment. We come up with a much simpler explanation of what the ant might be doing. And that simpler explanation, turn right if you're blocked on the left and vice versa, much easier to place in a machine. Okay. So, we just said that. This idea was first articulated by Valentino Breitenberg. Valentino Breitenberg wrote this great book called Vehicles in the 1980s. Breitenberg was not a roboticist. He was a neurophysiologist. He studied the architecture of brains in fruit flies. You've all lived in student dorms and student housing. You've probably seen lots of these things. Very, very small. And they will find any rotten fruit or any food, sugar products anywhere in the room. If I had a fruit fly here and there was a rotten apple in the back corner and let it go, it would fly around and gradually find the apple. In the 60s and 70s, when Breitenberg was most active in research, in the literature, there were theories about how fruit flies actually find rotten fruit, and people had ideas about how the fruit fly was performing differential calculus in its brain to follow gradients of smell and find the fruit. Meanwhile, Breitenberg was dissecting the brains of fruit flies. You know how small a fruit fly is. Imagine how small the brain of a fruit fly was. Breitenberg grew increasingly doubtful that there was some differential calculus built into these very small brains. Like the example of the ant, if you're a flying machine and you're moving about in air in three-dimensional space, if there is more smell on your left, veer to the left. If there's more smell on your right, turn right. If there's more smell in front of you, go forward. If there's more smell behind you, turn around. That's enough to follow a gradient to find the fruit. So Breitenberg realized by looking at the literature that people kept overthinking animal behavior. So he wrote this book called Vehicles, and he used the word vehicle on purpose. Although for us a vehicle suggests an artificial machine, vehicle in this sense is meant to represent an organism, a human, robot. It doesn't matter. It's something that can act on its environment and sense the repercussions of that action. In the book, it's written like a series of fairy tales. Once upon a time, there was a vehicle known as Vehicle 1. Vehicle 1 had a very simple body. We're looking above at Vehicle 1. It has a single wheel at the back and a single temperature sensor in this case. The temperature sensor is connected with a single wire to the wheel, which produces a pretty simple machine. If the temperature sensor senses higher temperature, the wheel spins at a faster velocity. Lower temperature, the wheel spins at a lower velocity. So imagine now what happens if you put this vehicle into a pond and you saw it swimming around in the pond. You might say it's restless because it does not like warm water. It is quite stupid since it's not able to turn back to the nice cold spot that it overshot in its restlessness. Anyways, you probably, if you didn't know what was going on inside the vehicle, you couldn't see whether it was made out of metal or cells. You might say, well, clearly it's alive, since you've never seen a particle of dead matter move quite like that. This was a highly respected neurophysiologist saying we would think something this simple is alive. Strange. Why use this kind of deliberately controversial language? We'll come back to that. The book continues on with a series of increasingly sophisticated vehicles. There's, I think, 12 in all. We won't look at all of them. Just look at the first few. Let's look at Series 2. So there's 2A and 2B, and these two robots are capable of fear and aggression. We now have a robot with 2 wheels, back left and back right, and 2 light sensors, front left, front right. And we have ipsilateral connections. Ipsa meaning the same, and lateral on the side. So we have same-sided connections. Left sensor to left wheel, right sensor connected to right wheel. Imagine now that you were to come at this robot from its front right with a flashlight. What would the machine do? Turn to the... Would it turn towards the light?
Get away from the light.
Turn away from the light? So it's going to turn away from the light. Why? Let's talk about sensor motor here. What's going on?
The light is more intense in this side.
On the right side? Yep.
So the wheel spin more faster. So
exactly. So at this instant in time, there's more light falling on the right-hand light sensor, meaning the right wheel is turning faster than the left wheel, and it turns a little bit away from the light. So let's sort of run our mental model of this machine. It turns a little bit away to the light. Let's imagine it just turns an inch or so. At the next time instant, assuming we do not move the flashlight, what happens now? It's turned a little bit away from the light. The robot has acted based on what it's sensed, which means the relationship between the robot's sensors and the flashlight have changed. This interaction has changed just because the robot moved. Right? This is what distinguishes robots from passive embedded devices. How does that change the robot's sensors? It's moved and there's been a sensory repercussion. What is that repercussion?
It's getting less light.
It's getting less light, right? It just turned away from the light a little bit. So now, given the change in the sensory circumstance of the robot, how does that change its action?
It's going to turn away from the light still, but a little more slowly.
It's going to turn away from the light a little bit more slowly because there's less light, which means it's going to be even further away from the light at the next time instant. It's going to turn, and slow down. Assuming that these light sensors are omnidirectional, it can still see the light behind it. I start chasing it with the flashlight from behind. What is the robot going to do as I start chasing it? So now the environment is fighting back. How does the robot react?
He will run away.
He will run away, right? Because he's afraid. He's the coward. If you read this chapter in Vehicles, Bradenberg tells us that, of course, this robot is the coward. It's afraid of the light. Is this robot afraid of the light? Why would a very serious and renowned scientist use such controversial language? Where's the fear circuit in this machine? It's not there. All right, let's leave that there for a moment. 2B, same thing, 2 light sensors, 2 motors, but now we have contralateral connections. We're going to literally cross the wires, contra across or against. Left sensor to right motor, right sensor to left motor, and let's assume the flashlight is here, pointing towards the robot's front left. What is the robot going to do in this case?
Move into the light.
Move towards the light. There's more light on the left sensor, which means the right wheel turns faster, which means the robot turns towards the light. What happens at the next time instant? Let's run our mental model of vehicle 2B.
Both sensors can see the light, so it starts approaching.
Both sensors can see the light, so maybe it evens out its turn and starts to head towards the light. So the curvature of turning is increasing. It's moving increasingly straight towards the light. What else is happening about the behavior of the robot? It's not just slowing its turn. It's speeding up, right? It's now closer to the light, which means the wheels turn faster. If instead of a flashlight you put a naked bulb on the ground, it will accelerate and smash the bulb because the aggressor hates light with a passion and will do whatever it can to destroy any light source that is naked and unexposed and at its level. Does the aggressor hate? Of course not, right? That's ridiculous. There's 2 contralateral synapses if we're thinking of this vehicle as an organism, or wires or circuit lines if we're thinking about a robot. Why would Professor Breitenberg talk about aliveness and cowardice and aggression?
I think he wants to explain those complex feelings using very simple mechanisms.
He wants to maybe not necessarily explain these complex emotions using simple mechanisms. What's the point he's trying to make aside from just vehicles?
Just simplify it in general.
Simplifying it in general, but how? He's making now a philosophical point. What is the philosophical point here?
Maybe that we put too much emphasis on what simple tasks.
We overthink things about animal behavior. Imagine that vehicle 1 and 2A and 2B were not machines but organisms, right? If you saw an organism doing something like this, you may or may not attribute an emotional state to it. The moment you open the hood of the vehicle and you see what's inside, well, of course, it doesn't have aggression or fear. Makes sense, right? It's just a machine. It can't possibly have these emotions. Remember our discussion about affective computing. There's one final point or one final step Professor Breitenberg wants you to take, right? Oh, of course, this is ridiculous. Machines don't have this. And maybe we overthink this in organisms. Lower organisms, at least. We do, though, right? Humans do, of course. We love, we hate. No question. No question that these don't, and no question that we do. What is the final philosophical point that Breitenberg is trying to make here?
We try to put ourselves into other objects, be it a small organism or a machine. We didn't know it was inside a machine. Say, how would that machine behave?
Right, we talked about this a few weeks ago, anthropomorphization, right? We project human values, or in this case, maybe human emotions, onto things like at least this vehicle that don't have them. What's the final point beyond anthropomorphization that Breitenberg is trying to push you towards? What's going on? We anthropomorphize ourselves, right? We project back onto ourselves. It feels like I have aggression and fear in the very same way that it feels like I decided to move my finger when I saw that moving red dot in the Libet experiment. The final point that Breitenberg was trying to make in vehicles is we should check our assumptions about our own emotional state, right? Do we actually have them? What do we mean? What do we really mean by fear and aggression. We overthink the behavior of animals, including potentially ourselves. Okay. As usual, we'll end on a philosophical point today. You have a quiz due tonight, and I will see you on Thursday.